Welcome to the A320 Autoflight lesson. In this lesson, you will gain a basic understanding of how the Autoflight system operates. You will also learn how to control and monitor the Autoflight system using its associated controls and indicators. The Autoflight system may be used to control the aircraft through all phases of flight. It is essentially comprised of three individual systems that work in coordination. They include two flight directors, which provide flight guidance displays on each PFD, two autopilots used to control the aircraft from initial climb to landing and rollout, and an Autothrust system, which provides the appropriate level of thrust throughout each phase of flight. The Autoflight system can be used at different levels. For example, the flight directors can be used to follow lateral and vertical commands, while thrust is controlled manually. The autopilot can fly the airplane while the pilot controls thrust manually. The Autothrust system can control thrust while the autopilot and flight directors are off. Or the flight directors, autopilots, and Autothrust can all be used simultaneously. The crew directly controls the Autoflight system using the following components: a dual-channel flight control unit, or FCU, which is the primary interface with the Autoflight system, and the multifunction control and display units, or MCDUs, which are used to enter and review flight management system data. On each side of the FCU are the EFIS control panels. Flight director push buttons on each EFIS control panel select the respective pilot's flight director on. Additional controls used during autoflight operations include both side sticks, which are used to manually control the aircraft in flight, and the thrust levers, which control engine thrust output. The status of the Autoflight system is monitored on the FCU and the primary flight displays, or PFDs. The flight mode annunciator, known as the FMA, on the upper portion of the PFD is the primary status indicator. Two flight management and guidance computers, or FMGCs, provide the Autoflight system with two functions: flight management and flight guidance. Flight management functions are used for lateral and vertical navigation, performance optimization, navigation radio auto-tuning, and display management. Flight guidance functions provide commands to the autopilot, flight director, and autothrust. Two flight augmentation computers, or FACs, provide the Autoflight system with flight envelope calculations, automatic turn coordination, and yaw damping. The MCDUs are the primary units for entry and display of FMS data. They are used for long-term actions such as flight plan entry and monitoring, performance monitoring, and vertical planning. Either MCDU can be used regardless of which autopilot is engaged. The Flight Control Unit, or FCU, is the pilot's primary interface with the Autoflight system. It is used to directly control autopilot and flight director speed, pitch, and roll modes. Four knobs on the FCU allow the pilot to make short-term mode changes. The knobs are spring-loaded to center, so after being pulled or pushed, they will return to a center position. Pulling one of these knobs allows a mode to be selected. When the Autoflight system is engaged in a mode that does not use FMS data, this is referred to as selected guidance. Pushing the knob reverts to managed guidance, with the FMS controlling the Autoflight system. Selected guidance always has priority over managed guidance. On each side of the FCU are the EFIS control panels. Flight director push buttons on each EFIS control panel allow each pilot to select the respective flight director on or off. The FCU incorporates push buttons to control various Autoflight functions. They include Autopilot and Autothrust push buttons, Localizer and Approach push buttons, and an Expedite push button. Press the Localizer push button. When selected on, the push button illuminates green. When a mode is selected off, the light in the push button extinguishes. There are 3 additional push buttons which are used to toggle between display settings. The Speed Mach push button switches the speed display between knots and Mach. The Heading Vertical Speed, Track Flight Path Angle push button changes flight director displays and Autoflight functions. While operating in heading vertical speed, rotating the heading knob selects the aircraft's heading. Rotating the vertical speed knob allows you to select a specific vertical speed in feet per minute for climbs and descents. When track flight path angle is selected, the aircraft's track can now be selected instead of heading. Also, a climb or descent flight path angle can be selected by using the vertical speed knob. Pressing the metric altitude push button displays the FCU's current selected altitude in meters on the SD. Selecting it a second time removes the indication. The side sticks are used to manually fly the aircraft. When an autopilot is engaged, both side sticks automatically center and remain centered even with autopilot flight control inputs. Each side stick is equipped with an autopilot disconnect push button. The thrust levers are used for manual control of engine thrust throughout the full range of forward and reverse thrust. Thrust can also be controlled automatically by the Autothrust system. To engage the Autothrust system, the pilot simply places the thrust levers within a specific range. For example, during takeoff, the Autothrust system automatically arms when the thrust levers are placed into either the toga or flex detents. The Airbus Autothrust system differs from other aircraft in that the thrust levers do not move in response to commanded changes. They remain in their detent position until moved by the flight crew. To disconnect the Autothrust system, 2 instinctive disconnect push buttons are located on either side of the thrust levers. Each pilot's primary flight display, or PFD, displays Autoflight information. The target airspeed and the FCU selected altitude are displayed on their respective indicator. The airspeed indicator also displays the aircraft's speed envelope with both the maximum and minimum speed bands. Deviation from the FMGC's vertical flight path is shown on the right side of the PFD. The flight director command bars are superimposed on the attitude indicator and display the commanded pitch and roll attitude. Each PFD also displays the flight mode annunciator. The flight mode annunciator, or FMA, is the primary method used for monitoring the modes and status of the Autoflight system. This mode information is provided by the master FMGC. The FMA is divided into 5 separate columns. The first 3 columns display the Autothrust mode, vertical flight guidance modes, and lateral flight guidance modes. The 4th column displays the aircraft's approach capabilities and entered decision height or minimum descent altitude. The 5th column displays the status of the autopilot, flight director, and autothrust. The lines of the first 3 columns follow a general rule. Engaged modes of the Autoflight system are shown on line 1, while armed modes are shown on line 2. Line 3 is dedicated to presenting FMS and flight control related messages. The information presented within the FMA will not be displayed unless at least one Autoflight system is engaged. For example, if Autothrust is active, but the flight directors are off and the Autopilot is disengaged, columns 2, 3, and 4 will be blank. However, columns 1 and 5 will contain information to support the active Autothrust system. If the Autothrust system is subsequently disengaged, the FMA will go blank. The FMA uses colors to aid in differentiating between each mode. Green indicates an engaged mode. Blue indicates an armed mode, as well as number presentations. Magenta indicates an armed altitude due to an altitude constraint. Red indicates significant flight control degradation. White identifies approach capabilities, as well as autopilot, flight director, and autothrust status. And amber, which identifies autothrust and flight control abnormalities. When changes are made to Autoflight system functions, a white box will appear around the FMA indication, highlighting the change. The white box appears for a short time and then disappears. There are two identical flight directors installed on the airplane. The flight directors display flight guidance information as command bars for the pilot to follow. Flight director guidance is generated by the two FMGCs. Guidance for Flight Director 1 is generated by FMGC1 and is displayed on the captain's PFD. Guidance for Flight Director 2 is generated by FMGC2 and is displayed on the first officer's PFD. When the airplane is on the ground and electrical power is established, both flight directors automatically engage. The command bars remain hidden but display as soon as takeoff power is set. In flight, or to re-engage on the ground, each flight director can be selected on using its associated push button. Press the captain's flight director push button. The captain's flight director is now engaged, and the FMA displays 1FD-, indicating only the number 1 flight director is on. Now, press the first officer's flight director push button. The first officer's flight director is now engaged, and the FMA displays 1FD-. To disengage the flight directors, simply press the FD push buttons. The lights extinguish, the command bars are removed, and the FMA indicates the associated flight director is disengaged. One important note: autothrust commands are based upon flight guidance. Flight guidance is active if either flight director is on. Therefore, when at least one flight director is on, the autothrust system assumes that the flight director is being followed. If the command bars are not followed, large speed deviations may occur. Therefore, it is important that pilots fly with both flight directors on or both flight directors off. The flight directors may be displayed in one of two modes: heading vertical speed or track flight path angle. Let's take a look at the heading vertical speed display. When the flight directors are on, pitch and roll commands are depicted as two green bars. The vertical bar, or roll command, provides active lateral guidance. As the command bar moves, the pilot should begin banking in that direction until the command bar becomes centered. The horizontal bar, or pitch command, works in much the same way. As the pitch command bar moves up or down, the aircraft pitch should be adjusted to follow the command bar movement. When the proper pitch and roll angles are achieved, The flight director bars will center on a box located at the center of the pitch reference symbol. The flight path vector symbol displays the flight path relative to the horizon. When the aircraft is in level flight, the symbol is centered on the horizon. When climbing or descending, the aircraft symbol moves above or below the horizon. As the aircraft turns, the symbol displays the appropriate bank angle on the PFD. To follow the flight guidance, simply maneuver to match the aircraft symbol with the command bar. The flight path vector symbol also shows the wind drift angle relative to the aircraft's heading. For example, with a crosswind from the right, the aircraft symbol shows the drift angle to the left. During takeoff and landing, the FMGC automatically tunes the flight plan runway ILS frequency and course, if available. The flight director system then uses the localizer to provide the flight crew with runway centerline guidance. The ground roll command bar indicates the position of the runway centerline. For example, if the command bar drifts left, the aircraft is right of centerline. When the flight director's pitch and roll command bars are not relevant, they are automatically removed from the display. Removing the flight director bars prevents the flight crew from receiving unnecessary commands and displays a less cluttered PFD for upset recovery. The roll command bar is removed when there is no lateral mode engaged, or when replaced by the ground roll guidance command bar. The pitch command bar is removed when no vertical mode is engaged, or during landing when rollout guidance is engaged. In certain situations, the flight director bars flash to alert the crew to a change of status to the guidance. For example, if the glide slope transmission becomes interrupted during an ILS approach, the pitch command bar will flash. This flashing continues permanently until a crew member changes the vertical guidance. Review the following chart that lists the conditions that cause flight director warnings. Occasionally, the FMA may display unusual modes. This may happen after an electrical power change, after engine start, or more commonly, after an aborted takeoff. To clear these modes from the FMA, both flight directors must be reset. Let's look at an example. You've just aborted a takeoff. The FMA indicates the Autoflight system is still in speed reference system and runway. Prior to performing another takeoff, the flight directors must be reset. This is accomplished by turning both flight directors off, then back on. Notice all FMA indications have cleared. The flight guidance modes have now been reset for takeoff. The Autoflight system has two autopilots. Autopilot 1 receives flight guidance commands from FMGC1, and Autopilot 2 receives commands from FMGC2. Each FMGC makes separate and independent computations. For this reason, only one FMGC will send guidance commands to the active autopilot. This FMGC is referred to as the master. The master FMGC is defined by which autopilot is engaged. If neither autopilot is engaged, FMGC1 defaults as the master. If an FMGC fails during flight, its respective autopilot is inoperative. In this situation, there is no automatic switching between FMGCs. An autopilot may be engaged by pressing either the Autopilot 1 or Autopilot 2 push button on the flight control unit. Press the Autopilot 1 push button. Autopilot 1 is now engaged. When an autopilot engages, the autopilot push button illuminates green. The associated autopilot indication displays on the FMA, and both side sticks are automatically centered. Each system operates independently. Only one autopilot may be engaged at a time. For example, if Autopilot 1 is engaged and Autopilot 2 is selected, Autopilot 1 disengages and Autopilot 2 becomes active. The autopilot can be disconnected by pressing the red disconnect push button on the side stick. When the autopilot is disconnected, the aural cavalry charge sounds, the master warning lights flash, and a red Autopilot off message displays in the right column of the memo section. To stop the cavalry charge, press the Autopilot disconnect push button a second time. This is the preferred method to disengage the autopilot, because the warnings will automatically extinguish without further pilot action. The autopilot can also be disengaged by pressing an illuminated autopilot push button or applying force to either side stick or the rudder pedals. Once again, the cavalry charge sounds, and the master warning lights flash. However, the messaging in the memo section is different. With these scenarios, a red Autoflight Autopilot Off warning message appears. These warnings continue until the side stick disconnect push button is pressed or the autopilot is re-engaged. On an ILS approach with a manual landing, aircraft limitations require that the autopilot be disengaged no later than 160 feet above ground level. On non-ILS approaches, the autopilot must be disconnected no later than 50 feet below the minimum descent altitude or derived decision altitude. For visual approaches, autopilot disengagement must occur no later than 500 feet height above aerodrome. There are a few conditions under which the autopilot will disengage automatically. During a non-ILS approach with the final approach mode engaged, the autopilot will disengage 50 feet below MDA or DDA, when in normal law and any of the protections are exceeded, when alpha protection is active, and finally, when both thrust levers are set above flex MCT and the aircraft is on the ground. The Autothrust system is controlled by the FMGCs. However, it operates independently from the autopilot and flight directors. Normally, the FMGC that controls the engaged autopilot also controls the Autothrust system. However, if no autopilot is engaged, FMGC-1 controls the Autothrust system. If the controlling FMGC fails, the opposite FMGC is able to automatically provide commands. If both FMGCs fail, the Autothrust system is inoperative. The status of the Autothrust system is either off, armed, or active. When the Autothrust system is off, thrust must be manually controlled using the thrust levers. In this case, the areas of the FMA dedicated to autothrust indications are blank. When the autothrust system is armed, thrust is set to a fixed value based on the thrust lever detent position. Autothrust can be armed either on the ground or in flight. On the ground, the system is typically armed when the thrust levers are advanced to a takeoff position, either flex or toga. In flight, autothrust is armed when the thrust levers are advanced to toga with the flap set to 1 or greater. The arm status is indicated by Autothrust displayed in blue in column 5 of the FMA, the FCU Autothrust push button illuminated green, and MAN displayed in column 1 of the FMA, along with the thrust lever position. The Autothrust system is now armed and will become active when the thrust levers are moved into an active thrust range. At the thrust reduction altitude, the thrust levers are set to the climb detent. The Autothrust system automatically switches to the active status. While in active status, the Autothrust system automatically varies thrust to meet the aircraft demands. Active status is indicated by the white Autothrust annunciation in column 5 of the FMA. During normal operations, active Autothrust status can only be engaged when the thrust levers are placed into the active range. In this mode, the master FMGC can command any thrust setting between idle and climb power. The active range is defined by how many engines are running. When both engines are running, the active range extends from just above the idle stop up through and including the climb detent. During single-engine operations, the active range extends from just above the idle stop up through and including the maximum continuous thrust, or MCT detent. During normal operations, autothrust becomes active when the autothrust system was previously armed and the thrust levers were placed into the active range, or autothrust is off, the autothrust push button is selected on, and the thrust levers are placed into the active range. The autothrust system uses two different thrust modes to provide automated thrust control. The two modes are fixed thrust and variable thrust. The operating mode of autothrust is determined by either the active pitch mode or the position of the thrust levers. Column 1 of the FMA is used to determine which mode is in use. If the autothrust system is off, column 1 will be blank. During fixed modes of thrust, thrust output remains constant or fixed. Airspeed is controlled with pitch. Fixed modes of thrust are used primarily during climbs and descents when a specific rate is not necessary. For example, during a climb, the autothrust system commands fixed climb thrust, the pitch of the aircraft changes to maintain airspeed, and the climb rate varies with aircraft performance. For descents, the autothrust system commands fixed idle thrust. Fixed modes of thrust are determined by referencing column 1 of the FMA. When autothrust is active, the route indication THR, followed by the appropriate thrust setting, specifically represents fixed mode indications. Thrust climb and thrust idle are two common examples. With thrust climb, the autothrust system provides fixed thrust equal to the climb thrust rating available for the current ambient conditions. As for thrust idle, the autothrust system provides fixed idle thrust. Some fixed modes of thrust are manually selected through specific thrust lever positioning. These modes are only present while the autothrust system is armed. Man toga and man flex appear when the thrust levers are placed to either the toga stop or the flex detent for takeoff. When a variable mode of thrust is in use, thrust output varies to maintain airspeed. A variable mode of thrust is used during climbs and descents when a specific rate is being maintained, as an altitude is being captured, during level flight, or when all flight guidance is selected off but autothrust is still active. The indications speed or Mach appear in column 1 of the FMA to indicate the autothrust system is using a variable mode of thrust. To see how a variable mode of thrust works, Assume the aircraft is leveling off from a climb. The autothrust system is currently in a fixed mode of thrust. As the aircraft levels to capture the target altitude, notice how autothrust automatically goes from a fixed mode to a variable mode. The thrust output decreases to maintain the target airspeed while in level flight. When autothrust is active, the position of the thrust levers limits the maximum autothrust authority. In normal operations, autothrust can never increase thrust above the position of the thrust levers. During normal operations, the thrust levers are placed into the climb detent and remain there until landing. This allows autothrust to increase thrust as needed up to a maximum of climb power. If the thrust levers are retarded toward idle, the active thrust range is reduced. This is referred to as thrust limiting. The upper limit is set by the current thrust lever position, and the lower limit remains at idle. As the thrust levers continue to move toward idle, the thrust envelope continuously decreases until idle is reached. When autothrust is active and the thrust levers are limiting, a level 2 caution is generated. Also, lever climb flashes in column 1 of the FMA, alerting the crew to return the thrust levers back into the climb detent. For the autothrust system to regain its full thrust range, the thrust levers must be placed back to the climb detent. Autothrust may be disconnected by pressing one of the two instinctive disconnect push buttons located on the thrust levers, or retarding the thrust levers to idle. When autothrust is disconnected, using either of these methods, the following occurs. A single chime sounds, the master caution lights illuminate momentarily, and an autothrust off message is briefly displayed. If an instinctive disconnect push button is pressed, autothrust disconnects and thrust immediately changes to match the thrust lever position. For this reason, the thrust levers should first be moved to match the current thrust output of the engines. This is performed by referencing the small white circles above the N1 indications on the EWD. These circles represent the actual positioning of the thrust levers. After the thrust levers have been repositioned, one of the instinctive disconnect push buttons may be selected, and autothrust will disconnect. The autothrust system will also disconnect when the autothrust push button is pressed, or if the system fails. Since these methods are not considered normal, a level 2 caution is generated if either of these two scenarios occur. Thrust lock is a feature designed to alert the flight crew that the autothrust system has disengaged in a manner that is not normal, either by the FCU autothrust push button being pressed or by a fault. When thrust lock is displayed, engine thrust is locked. It will not change until a crew member intervenes. If thrust lock occurs and autothrust is still functional, pressing the autothrust push button on the FCU may restore autothrust. If pressing the push button does not restore autothrust, the system has failed and thrust must be controlled manually. The thrust lock feature will continue to remain active until the thrust levers are moved. As soon as the thrust levers are moved, the thrust lock feature will disengage, and thrust must be manually controlled. Alpha floor is an autothrust feature designed to aid the flight crew in recovery from high angle of attack, low airspeed flight situations. This feature is available in all flight phases down to 100 feet radio altitude during landing. When alpha floor becomes active, the autothrust system automatically increases thrust to toga regardless of the thrust lever position or autothrust engagement status. In order for alpha floor to activate, the aircraft must be in normal yaw and the Autoflight system must be operational. Alpha floor displays on the FMA and on the engine warning display. When the conditions for alpha floor no longer exist, toga lock replaces alpha floor on the FMA. Toga lock is similar to thrust lock, except this time thrust is locked at toga. Normal operations can be resumed as flight conditions permit. Let's look at how to recover from alpha floor and restore the autothrust. First, place the thrust levers to the toga stop. This matches the thrust lever position with the actual thrust, preventing an undesirable thrust change. Next, press either instinctive disconnect push button to cancel toga lock. The autothrust system is now off and thrust must be controlled manually. To re-engage autothrust in an active mode, the thrust levers are moved to the climb detent, and the autothrust push button is pressed. Let's review how the different Autoflight systems work together. As you have seen, the master FMGC sends guidance commands to each of the three Autoflight systems: the Autopilot, the flight directors, and Autothrust. The flight directors display the flight guidance as dual Q command bars. These same commands are sent to the Autopilot, which then command the flight control computers to deflect the flight controls to follow the flight guidance. Because the commands are identical, the flight directors and Autopilot always engage in the same modes. For example, assume you are hand-flying the aircraft by following the flight directors and using Autothrust. Currently, the vertical guidance is in open climb, while the lateral guidance is in heading. If the Autopilot is subsequently engaged, it will default to the same guidance modes the flight directors are providing. Whenever the flight guidance systems are engaged, the autothrust system assumes that the flight guidance is being followed. To see how the systems work together, let's look at an example where the flight guidance is not being followed. Assume the pilot flying is hand-flying the aircraft. The flight directors are on, and the autothrust system is active. Currently, the aircraft is in a descent with autothrust in a fixed mode of thrust at idle power. Recall that with a fixed mode of thrust, airspeed is controlled by pitch. While in the descent, TCAS issues a corrective resolution advisory directing the aircraft to level off.
Reduce descent. Reduce descent.
The pilot flying responds to the RA by leveling off, but does nothing with the flight guidance system. The flight directors are still providing commands for the previous descent. Since the autothrust system assumes the flight director guidance is being followed, it remains in the fixed mode of thrust, providing idle power for the descent. Notice how the aircraft is now beginning to lose airspeed. Unless a crew member intervenes, the airspeed will continue to decay until additional autoflight and flight control system protections are reached. The previous scenario leads us to a very important lesson. If you are not going to follow the flight guidance system, it should be turned off. The reason is simple. When all flight guidance is removed from the aircraft, the autothrust system will then default to a variable mode of thrust. Airspeed will be maintained through power instead of pitch. To see how it works, let's look at the same scenario, but this time it's performed correctly. The aircraft is established in the descent with fixed idle power. Again, TCAS issues the same corrective RA directing the aircraft to level off.
Reduce descent.
The pilot flying levels the aircraft, but this time commands that the flight directors be turned off. Notice as soon as the last flight director is selected off, autothrust goes from a fixed mode to a variable mode of thrust, indicated by the word speed in column 1 of the FMA. If not previously engaged, the autopilot and flight directors will engage in default modes when selected on. The default modes are the same for each. While airborne, the default modes are heading and vertical speed. The modes may then be changed as needed to manage the aircraft's lateral and vertical flight path. Two flight augmentation computers, or FACs, compute flight envelope and speed functions for Autoflight use. Specifically, the FACs provide flight envelope computations, flight envelope protections, low energy warnings, and windshear detection. The FACs also provide rudder functions to include automatic turn coordination, yaw damping, rudder trim, and high-speed rudder limiting. While airborne, the FACs independently compute the aircraft's gross weight by using the angle of attack probes. The FACs then use this information to calculate the flight envelope for the aircraft. The characteristic speeds of the envelope are displayed on the airspeed tape of the PFD. These speeds include VMO/MMO, max operating speed, the maneuvering speeds, green dot, S and F speed, VFE for the next flap speed, VLS, lowest safe speed, alpha protection, alpha max, and the airspeed trend arrow. Alpha floor is also calculated by the FACs, but it is not depicted on the airspeed tape. Lastly, if the flight control system is degraded, the FACs also display VSW, or stall warning. If either FAC fails during flight, the other computer will automatically take over and display information on both PFDs. If both FACs fail, computed speeds are not shown on either PFD, and a red speed limit indication is displayed. At low altitudes, the FACs monitor airspeed and the flight path angle for low energy conditions. Low energy detection is active when the aircraft is below 2,000 feet and above 100 feet AGL. The flaps are in configuration 2 or greater, and alpha floor is not engaged. If threshold values are reached, an aural warning sounds.
Speed, speed, speed.
This speed warning is designed to alert the flight crew so they can preemptively act to avoid triggering alpha floor. The FACs are also responsible for detecting wind shear during takeoff and landing. These wind shear warnings are only available if the aircraft is below 1,300 feet AGL and configured at flaps 1 or greater. When wind shear is encountered, a red wind shear alert displays on the PFD and an aural alert is heard.
Wind shear, wind shear, wind shear.
The flight directors now command the appropriate guidance to recover from the wind shear. Flight guidance is provided for speed control, lateral navigation, and vertical navigation. This guidance comes in two types: selected and managed. Selected guidance is performed when the pilot directs speed, lateral, and vertical control. Managed guidance differs in that the flight management system provides the guidance commands. Generally speaking, both types of guidance may be simultaneously used for different functions. For example, you may be flying in a managed speed while manually selecting your lateral and vertical flight paths. Selected guidance is performed by momentarily pulling the associated spring-loaded knob on the FCU and setting the desired value. The selected values are then displayed in the FCU window. These values are also presented on the PFD and ND in the color blue. These indications, along with their associated FMA indications, are considered to be the best source for verifying that a selected function has been set. Managed guidance is performed by momentarily pushing the associated spring-loaded knob on the FCU. Any previously selected values are then replaced by dashes in the FCU window. Managed values are presented on the PFD and ND in the color magenta. These indications, along with their associated FMA indications, are also considered to be the best source for verifying that a managed function is being performed. Speed guidance is provided by the fax and is displayed on each PFD as a speed target triangle. The Autoflight systems use this airspeed target to acquire and hold a specific airspeed. The speed guidance modes and functions are controlled on the FCU. The pilot uses the speed knob and the speed mach push button to select the appropriate mode. Aircraft speed is controlled in one of two modes. The speed can be selected by the pilot by pulling on the speed knob, or the speed can be managed by the FMS by pushing on the speed knob. A selected speed allows the pilot to set a specific speed in the FCU. Let's take a look at how a speed can be selected. In flight, air traffic control has requested a speed of 250 knots. Pull the speed knob on the FCU to select a speed. The selected mode is indicated by a blue triangle and the current speed is displayed in the FCU window. Now, we'll set in a speed of 250 knots. The blue speed triangle moves to 250 knots. If the Autoflight systems are engaged, they will adjust pitch or thrust to satisfy the selected speed. Speed can also be managed by the FMS. Managed speeds allow for the FMS to optimize speed control and display the appropriate airspeed for the current phase of flight. Managed speeds are engaged by pushing the speed knob on the FCU. Managed speed is indicated by the magenta speed triangle and an illuminated managed speed mach dot next to the speed window. Managed speeds are available in each phase of flight. In most phases, managed speed requires at least one autopilot or flight director to be engaged. However, during approach, if the Autoflight system is turned off, managed speed continues to provide speed guidance during the approach and automatically selects the appropriate speed for the aircraft's current configuration. As altitude increases, speed guidance is referenced in terms of Mach instead of an indicated airspeed based upon knots. The altitude at which this switchover automatically occurs is based upon the aircraft's speed and happens in both managed and selected speeds. With a selected speed, the switchover is indicated by the FCU digital airspeed window changing from knots to Mach. When in selected speed, you may manually control the switchover using the Speed Mach push button. Press the Speed Mach push button. The selected speed now switches from Mach to knots, and you may now set your desired airspeed. To revert back to Mach, the Speed Mach push button can be pressed a second time. One unique feature is the Airbus's ability to manage speed during an approach. This allows the Autoflight system to automatically set the correct speed for the aircraft's current weight and configuration. When using managed speeds, you are protected from decelerating below the minimum speed for your current configuration. This means that deceleration will stop at the minimum speed for your current configuration. These speeds are automatically computed by the FMS and are shown on the perf approach page on the MCDU. The configuration speeds are shown here. In addition to F, S, and green dot speeds, a V approach speed is computed. V approach is the reference speed flown during final approach when fully configured for landing. It is automatically calculated by adding 5 knots to VLS, plus 1/3 of the steady-state winds entered into the MCDU. For example, if VLS is 130 knots, 5 knots is added, then 1/3 of the wind value, or 3 knots, is added for a final V approach value of 138 knots. Now we'll take a look at speed guidance as an approach is being flown. In managed speed, when the approach is activated, the aircraft will slow to green dot, the minimum speed in the clean configuration. When flaps 1 is selected, the aircraft will automatically slow to S speed, which is the maneuvering speed with slats extended. When flaps 2 is selected, the aircraft now slows to F speed, which is the maneuvering speed for both the flaps 2 and flaps 3 configurations. Since F speed is the same for both flaps 2 and 3, there is no change in speed guidance when flaps 3 is selected. When flaps full is selected, the aircraft will automatically slow to V approach. Ground Speed Mini provides wind shear protection by ensuring a minimum ground speed is flown during an approach. This protection ensures that sudden changes in headwind do not result in airspeed dropping below V approach. Ground Speed Mini is calculated by subtracting the runway headwind from V approach. As a result, entering the landing runway, as well as the steady-state winds, have an important effect on the calculation of Ground Speed Mini. Let's take a look at an example. The FMS indicates V approach at 145 knots, which includes a 10-knot wind additive because of the 30 knots entered in the wind field. Ground Speed Mini now assumes there will be a 30-knot headwind on landing, so the minimum ground speed on landing is 115 knots, V approach minus the headwind. This protection now commands an indicated airspeed which ensures that a ground speed of at least 115 knots will be maintained. If the winds are stronger than expected, indicated airspeed is increased to maintain a constant ground speed. By increasing the indicated airspeed, protection is now available so that if the unexpected headwind is suddenly lost, the airspeed will not drop below V approach. There is no direct indication of Ground Speed Mini. However, the effects can be seen on the airspeed indicator when the managed speed triangle moves to an airspeed which is greater than V approach. The lateral guidance modes allow the flight crew to independently control the aircraft's lateral flight path. These modes are selected on the FCU and include heading, track, managed navigation, and localizer tracking. Active as well as armed lateral modes are presented in column 3 of the FMA. Let's examine 2 different methods for selecting a specific heading. The pilot can select a specific heading by pulling the heading knob on the FCU. Once the heading knob is pulled, the aircraft's heading is displayed on the FCU, and a heading triangle indicates the selected heading on both the PFD and ND. Most importantly, heading is displayed on the FMA, indicating that selected heading is the current lateral mode. Rotating the knob adjusts the selected heading. With the autopilot engaged, the aircraft now turns left to the selected heading. This sequence of pulling the knob, then turning it to select a heading, commands the aircraft to turn in the direction of knob rotation. Now let's look at an example where the heading knob is selected first, then the knob is pulled. Even though the heading knob was turned to the right, the airplane will turn left in the direction closest to the selected heading. This method of pre-selecting a heading allows the desired heading to be set prior to starting a turn. When the heading is preset without pulling the knob, the value remains displayed in the FCU window for approximately 45 seconds. Instead of a heading, a specific aircraft track can be selected. press the Heading Track push button on the FCU. Track is now displayed on the FMA, and the heading triangle shifts to the current track. The track value can now be adjusted on the FCU. Managed Navigation, or Managed Nav, can be activated by pressing the heading knob on the FCU. Managed Nav allows the Autoflight system to track the flight plan entered in the FMS. Press the heading knob. When Managed Nav is armed, Nav is displayed in blue below heading in column 3 of the FMA. When Nav becomes active, Nav replaces heading. In addition, dashes replace the heading on the FCU, and a managed guidance light illuminates. The Localizer mode is used to track Localizer front course signals. The mode is armed by pressing the Localizer push button. Push the Localizer push button. The push button illuminates, and Localizer is now armed, indicated by the blue Loc in column 3 of the FMA. As the course becomes active, Loc star appears. Loc star indicates that the intercept has started but is not complete. When the star disappears, the Localizer has been captured and will be followed by the autopilot and flight directors. Vertical modes provide flight path guidance to the altitude selected on the FCU. Vertical guidance can be open and controlled by the flight crew, or managed and controlled by the FMS. The vertical flight path controls are on the right side of the FCU. Additionally, a specific vertical speed can be selected using the vertical speed knob. Let's look at each of the vertical guidance modes. Open mode refers to either an open climb or open descent, depending on where the FCU altitude is in relationship to the current altitude. If an altitude is set in the FCU that is higher than the current altitude, pulling the altitude knob will engage open climb. Open climb is essentially a climb where thrust is fixed at climb power. The aircraft increases pitch to maintain the commanded airspeed, and any altitude constraint on the MCDU flight plan will not be honored. If the altitude set on the FCU is lower than the current altitude, pulling the altitude knob engages open descent. When open descent is engaged, a descent begins with idle power at the commanded speed, and flight plan constraints are ignored. Let's look at an example of an open climb. Currently, the airplane is level at 7,000 feet. ATC has just cleared you to climb and maintain 11,000. 11,000 feet is selected on the altitude knob. To begin the climb, the altitude knob is pulled. Pulling the altitude knob engages an open climb as presented here in column 2 of the FMA. Thrust advances to climb power, and the Autoflight system uses pitch to maintain the commanded speed. The aircraft will continue in open climb until either another mode is selected or the FCU altitude is reached. Open descent works similarly. When a lower altitude is set and the altitude knob is pulled, the thrust is reduced to idle and the airplane's pitch is reduced to maintain the commanded speed. When climbing or descending, the Expedite push button can be used to increase the rate. During climbs, the Expedite push button initiates a climb at green dot airspeed and ignores all flight plan altitude and speed constraints. The FCU push button illuminates, and Expedite Climb displays on the FMA, indicating the Expedite mode is active. During a descent, pressing the Expedite push button increases the aircraft's airspeed to increase the descent rate. The airspeed increases to 340 knots, or 0.80 Mach, and the thrust decreases to idle. An Expedite mode will disengage when the FCU altitude is captured. If you must manually disengage an Expedite mode prior to FCU altitude capture, selecting the Expedite push button will have no effect. Instead, another vertical mode must be engaged. This can be performed by pulling the altitude knob for an open climb or open descent, pushing the altitude knob for a managed climb or managed descent, pulling the vertical speed knob for either a vertical speed or flight path angle climb or descent, pushing the vertical speed knob to level off the aircraft's climb or descent, or pulling the speed knob to select a speed. The vertical speed knob on the FCU can be used when a specific vertical speed is desired. Let's look at an example. The FCU altitude is set to flight level 270. Next, the vertical speed knob is set to the desired rate of descent of 1,000 feet per minute. Finally, to initiate the descent, the vertical speed knob is pulled. The aircraft now begins a 1,000 feet per minute descent to flight level 270, and all flight plan constraints are ignored. The vertical speed knob can also be used to level off during a climb or descent. Pushing the vertical speed knob sets the vertical speed to 0 and the aircraft levels off. The vertical speed knob can also be used to set a desired flight path angle. Setting a flight path angle is similar to setting a desired vertical speed, except that the vertical speed will automatically adjust to maintain the set climb or descent angle. To select a flight path angle, press the Track Flight Path Angle push button on the FCU. The vertical speed display now switches to flight path angle, and the current angle is displayed on the FMA and FCU. The remaining managed vertical modes are managed climbs and managed descents. Managed climb is activated by pushing the altitude knob and can only be active when managed nav is active. Managed climb is very similar to open climb in that the same speeds and autothrust settings are used. The difference, however, is a managed climb will honor any flight plan altitude constraints provided they're within the performance capabilities of the aircraft. Let's look at how a managed climb is used to honor an altitude constraint. ATC has cleared you to flight level 230, but has also requested that you cross Farmington at 9,000 feet. First, the constraint must be entered into the flight plan. Next, to begin a managed climb, the pilot flying presses the altitude knob. Notice Climb appears in column 2 of the FMA, indicating managed climb. Also, Alt is displayed in magenta, and 9,000 is displayed on the altitude scale. These indicate an altitude mode is armed due to the constraint. As the altitude constraint is being captured, altitude constraint star is shown, followed by an altitude constraint indicating the constraint altitude has been captured. Notice another managed climb is armed. The aircraft will maintain 9,000 feet until the waypoint is reached. After Farmington, the aircraft will resume a managed climb until either a different vertical mode is selected or the FCU altitude is reached at flight level 230. Much like a managed climb, a managed descent can only be performed when managed nav is active. A managed descent is slightly different than an open descent in that a pre-planned flight path is computed by the FMS. The FMS computes an idle descent flight path while accounting for speed and altitude constraints, as well as environmental conditions entered in the MCDU. In managed descents, the flight path has priority. Therefore, the airspeed is allowed to vary. Let's look at an example of how a managed descent is built by the FMS. Descending into Chicago O'Hare, there are two altitude constraints: Janesville at flight level 180 and Teddy at 10,000 feet. An idle flight path is computed from cruise altitude to the first altitude constraint at Janesville. This allows the aircraft to descend at idle thrust from the top of descent point down to the first constraint. This allows for the most economical path. Airspeed is controlled through pitch while the rate of descent is determined by idle thrust. Next, a geometric path is calculated between altitude constraints, allowing the airplane to descend at a constant descent rate between Janesville and Teddy. After the last altitude constraint at Teddy is reached, a geometric path descent continues and includes all the approach points as well as an approach deceleration point where the approach begins. The top of descent is indicated by a descent point. This arrow reflects where the idle descent path begins. The pilot may also reference the descent path indicator and the VDEV indication presented on the prog page of the MCDU. To begin a managed descent, a lower altitude must be set in the FCU. The pilot flying then pushes the altitude knob to activate a managed descent. Remember, managed climbs and descents can only be performed if the aircraft is in managed nav. They will not work while in heading or track. If the airplane is below the computed flight path, a 1,000 feet per minute descent rate is commanded until the flight path is intercepted. The point where the descent path will be intercepted is indicated on the ND. When the computed flight path is reached, the Autoflight system commands the required vertical speed to maintain the flight path. If the aircraft is above the computed descent flight path, it will pitch down toward the upper limit of the managed speed range. If the resultant airspeed increase is not sufficient to recapture the flight path, a more drag message is displayed on the PFD. This indicates at least 1/2 speed brakes is required. If this is still insufficient, the MCDU will display an altitude error or speed error message. During a managed descent, the airspeed may be selected. If the selected speed is faster, the autothrust increases thrust to maintain the selected speed. If the selected speed is slower, the airplane may deviate from the computed flight path, as the selected speed now has priority. In either case, a managed descent is maintained until an FCU altitude is reached or a different vertical mode is selected. During a level-off transition from a climb or descent, the altitude star mode occurs. It is indicated by alt star in column 2 of the FMA. The altitude at which alt star occurs depends on the aircraft's vertical speed. The greater the aircraft's vertical speed, the earlier altitude star is activated. Altitude hold is used to maintain a specific altitude, and is indicated by alt on the FMA. In altitude hold, the FCU altitude and vertical speed displays can be modified, but will not be acted upon until a new vertical mode is selected. During cruise, To minimize thrust variations and reduce fuel consumption, a soft altitude hold mode is used. This mode allows the aircraft's altitude to vary slightly from the cruise altitude as referenced from the MCDU prog page. When in the soft altitude hold mode, Alt Cruise is displayed on the FMA. Vertical mode reversions are used by the autopilot and flight director system in the event that the aircraft is approaching a flight envelope limit. There are essentially three reasons for an automatic mode reversion. When vertical speed is active and the aircraft cannot maintain the commanded rate and the selected airspeed, when an illogical FCU altitude is set, or to prevent the aircraft from exceeding a flight envelope limit while manually flying the aircraft. As discussed earlier in the vertical speed mode, the Autoflight system honors the selected vertical speed, while the Autothrust system controls thrust to maintain airspeed. During climb, if an excessive climb rate is set, the aircraft's airspeed will eventually decrease. If this decrease continues without pilot intervention, it may eventually reach VLS. As VLS is reached, the Autoflight system will automatically intervene by reverting to open climb and accelerating the aircraft toward the managed speed. During descent, the system functions in much the same way. If an excessive rate of descent is set, the aircraft's airspeed will begin to increase. As the acceleration continues, it eventually approaches Vmax. To prevent Vmax from being exceeded, the autopilot commands a pitch up to slow the aircraft. The Autoflight system uses logic to ensure it is in the correct mode when a new altitude is set in the FCU. For example, if you are in open climb and a higher altitude is set, the aircraft will continue in open climb. However, if the set altitude is in the opposite direction from the commanded mode, vertical speed will automatically activate and the aircraft will continue at the current vertical rate. Since 10,000 feet is below our current altitude and open climb is active, the aircraft automatically reverts to vertical speed and the vertical rate at the time of the reversion. This reversion most commonly occurs when the FCU altitude is changed in Alt star. Anytime the altitude is changed when acquiring an altitude, vertical speed becomes the active mode. If this goes unnoticed by the crew, the aircraft could continue with a vertical speed that is undesirable. While flying the aircraft using the flight director, the command bar should be followed to avoid a potential speed deviation. Remember, in a climb mode, the thrust is fixed to climb power. During an open descent, thrust is fixed at idle. In both modes, the thrust will not vary to maintain airspeed. The flight directors command a pitch attitude to maintain airspeed. If the airspeed approaches either Vmax or VLS, the flight directors will automatically revert to the vertical speed mode. In vertical speed mode, the Autothrust system changes from the fixed thrust to speed mode. Now, the Autothrust system can vary the thrust to attempt to keep the airspeed within the flight envelope. Let's take a look at other common flight guidance modes. These modes also provide both lateral and vertical flight guidance. While on the ground, the default mode for the flight directors is climb and nav. This allows the flight directors to provide correct flight guidance on takeoff and initial climb with little action from the flight crew. During takeoff, when toga or flex thrust is applied, the Autoflight system automatically engages in the following modes. SRS, or Speed Reference System, becomes the active vertical mode, and runway becomes the active lateral mode. Let's look at each mode individually. An SRS climb is designed to provide the correct pitch attitude after liftoff. During a normal takeoff, with both engines operating, the flight director and autopilot, if engaged, provide a pitch attitude to maintain V2 plus 10 knots. The speed reference system is also designed to provide proper pitch guidance in the event that an engine fails. During an engine failure, pitch commands provide a speed of V2 or the aircraft's current speed if higher. In both scenarios, SRS will remain active until acceleration altitude is reached. SRS can also be disengaged by engaging any other pitch mode, such as vertical speed, climb, or open climb. During takeoff, if the departure runway has an associated localizer, runway is the active lateral mode. This mode uses the localizer signal to provide lateral guidance during the takeoff roll. After liftoff, if a heading was pre-selected prior to takeoff, runway track automatically activates. In runway track, the autopilot and flight directors provide roll commands to maintain the extended runway centerline track, automatically compensating for any wind drift. Runway track will remain active until a different lateral mode is selected. An ILS approach uses the localizer for lateral guidance and the glide slope for vertical guidance. The approach can be flown using either one autopilot or, for additional redundancy, both autopilots. Once cleared for an ILS approach, pressing the approach push button on the FCU arms both the localizer and glide slope modes. Press the approach push button. The second autopilot can only be engaged after the approach push button is pressed. Engage the second autopilot. Both autopilot push buttons are illuminated and the FMA indicates Autopilot 1 plus 2. The aircraft will now capture and track the localizer signal as indicated by Loc star followed by Loc. As the glide slope becomes captured, it is indicated by glide slope star followed by glide slope. The autopilot and flight directors now use aircraft pitch to maintain the glide slope. As a descent begins, any FCU altitude will now be ignored, and if desired, a missed approach altitude can be set. During an ILS approach, once the approach push button has been pressed, the Autoflight system will begin self-monitoring. The aircraft's current approach and auto-land capabilities will be presented in column 4 of the FMA. These capabilities include Cat 1, Cat 2, or Cat 3 operations. Let's briefly look at each. A Cat 3 dual annunciation indicates that both autopilots are engaged and the system is in a fail operational condition. A fail operational condition indicates that all of the monitored systems have redundant capabilities, and if there is any system failure, an auto-land is still possible. If the approach capability downgrades for any reason, the flight warning computers provide an oral indication. Cat 3 single is now displayed on the FMA. Cat 3 single indicates the system is in a fail passive condition, which may occur when only one autopilot is engaged, or one or more systems have lost redundancy, such as an inoperative yaw damper. During fail passive operations, if there is a failure of a system, an auto-land will not be accomplished and the landing must be flown by the pilot. When Cat 3 operations are unavailable, this is typically indicated on the status page as shown here. In this case, Cat 2 is now displayed on the FMA, and Cat 3 and Cat 2 approaches are not authorized. If neither autopilot is engaged, Cat 1 is shown on the FMA, indicating the current approach capability. During an ILS approach, if both autopilots are engaged and approach capabilities exist, an auto-land may be accomplished. If neither autopilot is engaged, Cat 1 is shown on the FMA, indicating the current approach capability. During an ILS approach, if both autopilots are engaged and approach capabilities exist, an auto-land may be accomplished. There are specific wind limitations for executing auto landings. Headwind limited to 30 knots, crosswind limited to 20 knots, tailwind limited to 10 knots. Let's take a look at the airplane's profile as it continues down the glide slope. At approximately 400 feet, the land mode engages and replaces both the localizer and glide slope modes on the FMA. Once the land mode is engaged, the only way to disengage the mode is by selecting toga thrust on a go-around or by disconnecting both autopilots and both flight directors. As the approach continues, at approximately 40 to 50 feet, the flare mode engages. The aircraft now begins to pitch up for touchdown, and if a crosswind exists, will align the aircraft's heading with the runway heading, landing in a wing-low attitude. At 10 feet, the autothrust system begins reducing thrust, and retard is automatically called out, indicating the pilot should retard the thrust levers to idle.
Retard. Retard. Retard.
After touchdown, the rollout mode engages. During rollout, the localizer signal is used by the autopilot to steer the nose wheel to keep the airplane centered on the runway. Braking is automatically accomplished by the auto brakes. An auto-land system failure is indicated by the illumination of the auto-land lights on both sides of the glare shield. The light will illuminate when the aircraft is in land mode below 200 feet and one of the following occurs. Both autopilots fail, the localizer or glide slope signal is lost, a significant difference exists between the radio altimeters, localizer deviation exceeds a quarter dot, or glide slope deviation exceeds 1 dot. During a non-ILS approach, the FMS can provide both lateral and vertical flight guidance. The approach nav mode provides lateral guidance, and the final mode provides the vertical flight guidance. These modes are selectable when a non-ILS approach is entered in the MCDU flight plan. They are armed by pressing the approach push button on the FCU. Press the approach push button. Approach nav will engage once the approach course is intercepted. The final descent is indicated by the blue Resume Descent arrow on the ND. Once the airplane intercepts the vertical profile and is on the final approach course, final mode engages. When this point is reached, the airplane begins a managed descent down to the MDA. Final approach is displayed on the FMA for both the lateral and vertical flight modes. The descent continues to 50 feet below the MDA, at which point the autopilot will automatically disengage. Heading and vertical speed become the active modes. During a go-around, autoflight guidance is similar to that of a takeoff. The aircraft automatically enters the go-around phase when the thrust levers are advanced to toga and the flaps handle is at 1 or greater. During the go-around, the autopilot, if engaged, will remain engaged and the flight directors will provide pitch and roll guidance. SRS becomes the active pitch mode and targets the current airspeed or V approach, whichever is higher. During a go-around, SRS remains active until the go-around acceleration altitude, typically 1,500 feet AGL. The active lateral mode is go-around track. Go-around track commands the existing ground track at the time go-around is engaged. It can be disengaged when a different lateral mode, such as heading or nav, is engaged. That is incorrect. That is correct. That is correct. That is correct. That is incorrect. 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 That is correct. That is incorrect. That is correct. That is correct. That is incorrect. That is correct. That is correct. That is incorrect. That is incorrect. That is incorrect. That is incorrect.